Welcome to the MAA-AMC Curriculum Inspirations session number 1 from Fabulous Math Fest. Thank you for the MAA for bringing great joy to the world in matters of mathematics. So I absolutely love the AMC for the mathematical content that appears in the various problems. I don't know if you take the competitions or not. I'm not particularly a competition person myself, but I do love the mathematics that's in these competitions. It's amazing. And I want to talk about my human reaction to doing competition problems or any problem in mathematics or any problem in life for that matter, because I am a very human being. So let me start off with something that's not actually competition worthy, but let me just make a point. Suppose I had a little school book exercise like this. Here's a very interesting, well, completely uninteresting school book problem. Please compute 7 3/4 divided by 10 1/3. There's just a pure textbook problem, nothing to do with competitions. But here's the point I want to make. Whenever you're faced with a challenge in mathematics or life, I say there are 2 fundamental first steps. 2 of them, 2 first steps. Step number 1, be your honest human self and have an emotional reaction and acknowledge your human reaction. When I see a problem like this, here are my honest human reactions. Number 1 is ick. Who wants to work with dividing mixed numbers? Ick, ick, ick. Another action is why? Why does anyone want me to do this? Why would I even want to do it? Anyone? What's going on? So maybe my other reaction is I don't care. I don't care what the answer is. So I'm being my honest human self. I'm having my first step is have an emotional reaction. Some people don't have to be just negative reactions. Could be like positive reactions. For example, oh my goodness, I love playing with mixed numbers. Bring it on. So it could be a reaction of joy. Whatever your human reaction is, have it. Step number 2. Take a deep breath and do something. Attend to it. Do anything. So here's the thing. I'm going to shock school teachers all across the planet because I'm a citizen of the 21st century. Here's the first natural thing I would do. If my goal is to get the answer is, here it comes. I'm going to show you what I would actually do. Get out my smartphone. If my goal is to get the answer, then I'm actually going to do it. I'm going to do 7.75 divided by, was it 10? 3. That's probably enough. I'll do a few more 3s. Why not? Just do it on a calculator and I get, whoa, I get 0.75. I get 3/4. Whoa. So actually my emotional reaction has now changed. I go, is it possible that actually that horrible ratio of mixed numbers is 3/4? That's now intriguing. All right. So let's see if I can do it now. Let me see if I can just think my way through. So I'm just illustrating the process of solving problems with a school book fraction problem. Okay, so what I see here, well, I don't like what I'm seeing. In fact, I don't like seeing fractions within fractions. So here's another strategy. If you don't like what you see, change it in a way that makes sense. For example, I don't like fourths in the top line. And one way to get rid of fourths is to multiply everything through by 4. But there's a consequence. If I multiply the top line by 4, I better keep the fraction balanced and multiply the bottom line by 4 as well. So actually, I can say, all right, that's going to make things a bit simpler. So I get 4 times 7 is 28 on the top line. And 4 times 3/4, that'll be just 3. So I get 28 plus 3 on the top line. And on the bottom line, I'll get 4 times 10 is 40. And on the bottom line, I get, 4/3. 4/3. I still got fractions within fractions. I don't like fractions within fractions. So I say to myself, well, if you don't like something, change it. Change it. I don't like the thirds. Change it. Multiply everything by 3. But consequences, better keep things balanced. Multiply everything by 3 on the top line. So this is actually equal to this now. 28 times 3, 60 plus 24, that's like 84 or something. 84 plus 9. And on the bottom line, I get 120 plus 4/3 times 3. I'm off the page a little bit. 4/3 times 3 is 4. So I'm getting, what's that? 93 over 124. Ew, that's still icky. That's still icky. Is that really 3/4? I mean, at least I've got whole numbers now. I'm not dealing with fractions within the fractions. But then I say, if I'm thinking 3/4, to me, this is 3 times 31. I can actually see it's 3 times something. Is this 4 times 31? Lo and behold, it is 4 times 31. 31's cancel, and there it is. It is actually 3/4. So this little school book problem shows the technique of problem solving. Yes, something can look scary. Be your honest self. It's okay if an emotional reaction, be it a positive one, a negative one, be intrigued, be delighted, be scared, be nervous, whatever it is, acknowledge your human self, and then try doing something, anything. Actually try it on a calculator, though you might not have one around, try something else, and the parts you don't like, change them. Keep changing things, do get something you do like that might guide the way. So this is a session on AMC problems, not school book problems. So let's do an actual AMC problem. Let me show you my emotional reaction. Let's go through the whole experience of problem solving. So here's a problem. Okay, I wrote these things out by hand because, well, you see my technology techniques are very low key. This is from 2020. This is last year's AMC 8, problem number 18. Rectangle ABCD is inscribed in a semicircle with diameter FE. Okay, geometry. Geometry is always hard to read because I've always got like lots of complicated diagrams, all the points labels things. So I've got A, B, C, D. Where is it? A, B, C, D. There it is. There's A, B, C, D with diameter FE all the way across. Okay, as the picture suggests, that's probably the diameter. Got it. Let DA be 16. Okay, I'll let it be 16. DA is 16. There, I'll let it be 16. Let FD be 9. Where's FD? Oh, that little bit is 9, already labeled. Cool. AE to be 9. Got that as well. Great. And the question is, what is the area of the rectangle ABCD? All right, okay, so I'm going to follow my actual human steps. You're getting to see James Tanton's brain today when it comes to competition problems or any problem. First step, have an emotional reaction. My emotional reaction is I actually personally don't like geometry. I find it really complicated to read stuff like this. Oh, but my other reaction is I actually like pictures. So actually, maybe I do like geometry problems. If I want to get past all the details and the picture's properly labeled, I like it. So I guess I'm kind of intrigued. And of course, my eye went to that rectangle. I think I want to get information about that rectangle. So this problem is aligned to where my brain wanted to go with that picture. So my emotional reaction is, okay, this could be interesting. Could be interesting. Take a deep breath. You just heard me take a deep breath. Do something. Step 2 in problem solving is to do something. Now, I'm not quite sure what I'm going to do here. Actually, here's a very good do something. List the things it's about. List things it's about. That's often a very good do something. At least, you don't have to write it out, but I'm going to do it in words. It's definitely about circles. It's definitely about rectangles. It's definitely about geometry. I can list all the things it's about, but actually, having done that already, that's about circles and diameters. I guess most people actually like about the radius of circles. Most people talk about radius. In fact, all the formulas about circles, circumference is 2 pi r and area is pi r squared. It's all about the radius. Do I know the radius in this question? So here it is. I'm doing something. I don't know if the radius is relevant, but I'm wondering if I know the radius. And I guess I do because they told me that FE was the diameter. So the radius is half of that, which would be half of 9 and a 9 and a 16. Oh, half of a 9 and a 9 is a single 9. Half of a 16 is an 8. So that must be an 8 and an 8 there. That must be the center, and the radius must be 17. 9 plus 8, 17. So you're just seeing how my brain's working. I now know the radius of the circle is 17. The question is, I don't know if that's relevant or not, because that's got nothing to do with the question. What am I meant to be doing? Find the area of that rectangle. Now, I'm sure you are cleverer than me and have probably got the answer already, and that's fine. And if I could see the chat, I'd invite you to write your answers in the chat, but I can't see the chat. So I don't know what you're thinking or saying or doing, but if you want to share your answer with the world, feel free. If you're shy like me and don't want to share your answer with the world, that's fine. Don't share it with the world. We're all humans. We all do our different things. But the thing is, I've just worked out the radius. I don't know why, because I was just doing something. I wasn't even like pretending to the problem. But I do want the area of the rectangle. I know it is 16 wide. 8 plus 8 is 16 wide. I guess I need this height. And I don't know the height. I only know the radius. So what can I possibly do? Well, it seems like I want to draw the radius. I mean, I've got a radius there. I've got a radius there. It seems tempting and irresistible. In fact, I want to draw a radius there. And I know that's 17. And then suddenly things might actually fall into place. That was just me just flailing right there. I just drew in another radius. And suddenly I see a right triangle, 8, 17, and h. Oh, that's a little right triangle. Yes, a right triangle. So Pythagoras says that h squared plus 8 squared is 17 squared. Oh, bingo. I think this is working out. H squared plus 64 is 289. Oh, golly gee, is that right? I don't know. 17 times 17, that feels like it's 289, something like that. Must be. So h squared is 289 take away 64. That's 225. And I bet that's a nice one. I bet that's 15 squared because I bet the author of this problem is being nice to me and choosing nice numbers. I bet the height is 15. 15 times 15, that does feel like 225. Yep, that's good. That's good. What was the question? Oh, find the area. I'm still not there yet. I found the radius. I found the height. I haven't found the area. The area is height times width. 15 times 16. So that's 15 times 15, the 225, plus another 15 makes 240. The area is 240. Beautiful. Is that the answer you got? Grand and good. But the point of this session is just so you can see what my brain is like. Okay, I answered the question. Great, fine, good. However, I'm more intrigued by this question because it actually invites more from me. Every question answered is an invitation for more. For example, I will tell you another emotional reaction I had was it's kind of annoying that we only had half a circle. I'm so used to drawing full circles in geometry, in which case it makes me think of wanting this sort of picture. Why not make it a picture of the full circle? In fact, let me draw it here. So now I'm actually saying, okay, I'm now thinking I want a picture of the full circle. And that means I'm going to have a full rectangle. I believe that was 9, that was 8, that was another 8, that was a 9. And this is the radius and so forth. That was the height I was trying to work out. So that's 16, that's 16. I could try to work out h from that picture. In fact, I can see that 2 h's is this picture. Do you know what? I actually think this is really exciting. I really love this picture. I think this is a cool way to think about it. So this is just my brain. So I'm just sharing with you my strange Tanton brain. I happen to have about 40 years of experience thinking about mathematics. And there's one of my favorite results in geometry that I think is just intuitively, stunningly surprising. It's this one. Ptolemy, back in the year 200 or so, discovered that if you take one chord and you take another chord, they don't have to be diameters, any 2 chords, work out this length A and this length B. So split into a length A and a length B. Work out this length C and this length D. So this chord is split into C and a D. It's absolutely amazing that the product of A and B, how that chord is split, always equals the product of C times D, how the other chord is split. Any 2 chords in a circle always split themselves into lengths that have the same product, to which I think, whoa, that is an amazing result. I think that's really, really crazy. In which case, that's exactly what I've got going on here. I've got one chord here that's split into a length of 9 and a length of 25. And another chord here that I want, which is split into length h and a length of h. So this big result in geometry I happen to know is that h times h, that product, h squared, would have to be this product, 9 times 25, 9 times 25. Oh, h squared is 3 squared times 5 squared, so h must be 3 times 5, which is 15, which is, I think, what we had before. Is it? Where was it? Yes, we had h was 15. Whoa. So actually, every question solved is an invitation for further thinking. I happen to go to another result in geometry I knew, which I think is beautiful, and I see I can even use that result right there. But of course, every question solved is an invitation for further thinking, because now I'm saying, okay, there was a rectangle from a circle of radius 17, the radius was 17, as a rectangle of area, what do we say, 240, I think it was? Well, of course, the natural question I want to ask now is, what other areas could rectangles be inside a circle of radius 17? In fact, what's the area of the biggest rectangle I can fit inside of a circle of radius 17? Now I'm on an exploration of cool stuff. I want to keep going further with that question. I like that question. This is great. This is why I love the mathematics in the AMC. It's got really deep invitations to joyous thinking. Wow. Okay, so this makes me want to do another question. Let's do another question. I'm having fun. I'm sorry I can't see the chat. I'm sorry I can't interact with you in any way, shape, or form. So I'm afraid this is just the experience of listening to James Tanton as he rattles away, doing AMC problems. Here's one that has me scared already, just by the sheer volume of words. So my first emotional reaction before I even read anything is, I am scared. Even just reading this is going to take me 10 minutes, not just be able to solve it, whatever the question is. But again, this is from last year. It's problem 16 from the AMC 10. Let me try to read it out loud because I'm sure my handwriting is atrocious. Here goes. Baylor and Jen, by the way, they are real people that work at the MAA, Baylor and Jen. They play the following game on the closed interval 0 to n on the real number line where n is a fixed integer greater than 4. Okay, so what am I doing there? I'm already lost. Before I do anything, let me just draw a picture. I like that strategy, draw a picture. So we've got the number line. I can do that. I saw the word number line. Didn't I see the number line? Yeah, the real number line, yes. So I'll draw the number line. At least I'm going to do that. So I'm nervous. My emotional reaction is nervous. Taking a deep breath. I'm still going to do something nonetheless. I'm going from 0 to n. So there's 0 on the number line and some integer n on the number line. So I'm on that interval between 0 and n, and where n is at least 4. So it could be like 4.5 or 17 or 226, done between 0 and n on the number line. Okay, so far so good. Baylor and Jen. They then take turns playing with Baylor going first. So what are they playing? At his first turn, Baylor chooses any real number in the interval. So Baylor just chooses a number. Baylor says, I choose this one, whatever it is, 1.76 or something. All right. Thereafter, the player whose turn it is chooses a real number that is more than 1 unit away from all the previously chosen numbers. So then it's Jen's turn. She has to choose a number that's at least 1 way from that, maybe like way over here. She keeps away. Then Baylor has the turn to choose a number at least 1 unit away from anything on the board so far, maybe there. And then Jen says, I can squeak one in right there. And then Baylor says, oh, I don't think I can squeak one anymore. The player unable to choose such a number loses. All right, so they keep putting points on that number line between 0 and n, making sure each number they choose is at least 1 away from anything else on the board so far. Okay, what's the question? There's no question yet. Okay, all right, what's the question? Here goes. The question keeps going, more reading. Using optimal strategy, which player will win the game? Baylor will always win. Jen will always win. Baylor will win only if n is odd. Jen will win only if n is odd. Jen will win only if n is bigger than 8. Okay. I am definitely having an emotional reaction to this question. It's making me panic. First of all, look how long it is. Just reading it took me for that long. Trying to make sense of what I read is still a little bit nebulous in my brain. We've got some interval between 0 and n, and people take turn choosing points in that interval until someone wins. Do you know what? I don't know what n being bigger than 4 has to do with anything. I guess I want n at least 1, because if n was 1 and they had to be 1 away from everything, that would be hard. So I don't know what the size of n has got to do with anything. Do you know what? Okay, I'm going to be really bold. I just said I don't believe the size of n has got to do with anything, which means I don't believe anything is about that depends on n has got anything to do with anything. I'm going to be bold and say I bet none of those are relevant. Whoa, how's that for bold? I'm trying to second guess the author now, which is another strategy. Can you second guess the author and eliminate incorrect choices? Yeah, I think I'm going to eliminate those ones. I can't imagine how this game changes with n equals 7 versus n equals 8, or n equals 8 versus n equals 9. I don't think even or oddness has anything to do with it. I don't think bigness has anything to do with n. So I think Baylor will either always win or Jen will always win. I think it's going to be one of those two choices. Great. All right, but what can I say here? Using optimal strategy, which player will win the game? Can Baylor, who goes first, always win? Or can Jen, who goes second, always win? All right, so this is where, I'm a mathematician. I can't think fast. My brain doesn't think fast. At this point, I'd probably go for a walk. Bit tricky when you're taking a competition exam where you're not meant to sit in your desk, but I like to go for a walk and think about mathematics. And this one will probably be one of those things. I'll let it sit in my brain, rattle in my subconscious for a while, rattle in my conscious for a while. And then I realized there's actually something interesting about this game. It's not symmetrical. Baylor gets to go first. And then I bet Baylor could do something really interesting, because there seems to be some interesting point in this game. In fact, I can't remember what I did first, but here we go. Here's the game. Let me draw the interval again. We're between 0 and n. And Baylor gets to go first. It seems pretty, something special about this point, the midpoint. That just seems to be screaming me in the face. If Baylor chooses the midpoint first, if Baylor goes there first, then Jen will do something. Oh, Jen will do something. She might go, she has to be, remember, at least 1 unit away from it, so maybe she goes over here. So maybe Jen will go there. But you know what? Baylor is then certain to be able to do another move. He could just do the symmetrical version of Jen's move. Maybe Baylor will then go there next. Oh, and then Jen says, okay, I can still squeeze one in here. Jen. But because everything's being kept symmetrical, Baylor can keep playing symmetrically and copy what Jen did, but on the other side. So if Jen is still able to move on one of these sides, Baylor will always be able to copy it on the other side. Baylor can always copy Jen. That means if Jen was able to move, then Baylor's able to move. The only thing can happen is Jen has to be stuck first, because if Jen was not stuck first, then Baylor could follow with another move. I think Baylor always wins. If he plays this way. How's that for terrible handwriting? I can't even read my handwriting. I can't even read my handwriting. But Baylor will always win. Baylor will always win. Whoa, whoa. Okay. So again, I'm illustrating some strategies of problem solving. Again, the two fundamental strategies. One, be your honest human self, acknowledge your emotion. I mean, this was intriguing. One of my emotions was intrigue, but my first emotion was scared. Just even reading this question was too much. But then we did something. We drew a picture. We saw what's going on there. We also eliminated some choices that might not be correct. That's a good strategy. Always eliminate some incorrect choices or things that could be likely be incorrect. And then we also took a deep breath and just played. And we played with the idea that there seems to be some extreme position. Not extreme in the sense like far off to the left, far to the right, but this middle seems to be special about the game, whatever the middle is. Go to the special place, and maybe that can be enlightening. So there's actually several strategies there that sort of come into play for problem solving, which then suggests, let's do another one. Let's do another one. Let's try this. Here is a next question. I went back a few years this time, and I found this one. I found this question. Again, there's a lot to read here, so let's see how this goes. It's from 2017. Whoops, you can't see it. The camera's gone off the screen. There we go. From AMC 8, and it's problem 24. Mrs. Sanders has 3 grandchildren who call her regularly. So 3 grandchildren who call her regularly. One calls her every 3 days. One calls her every 4 days. And one calls her every 5 days. Okay, these are very regular grandchildren. One calls every 3rd day, one calls every 4th day, one calls every 5th day. All 3 called her on December 31st, 2016. Okay, so just before, on New Year's Eve, they all called her, and then throughout the year of 2017, by the way, not a coincidence, that's the year of the competition, all through the year 2017, one called every 4 days, one called every 5 days. What's the question? On how many days during the next year did she not receive a phone call from any of her grandchildren? Okay, which of the days had no phone calls? All right. Step 1, have an emotional reaction. What's my emotional reaction here? I'm a little bit nervous. I'm always nervous about these sorts of things when I have to operate under pressure. I'm also intrigued by this one. For some reason, this one appeals to me. I don't know why it appeals to me, but I'm intrigued. So that's my emotions. I've got 2 emotions. I'm nervous and I'm intrigued. Step 2, take a deep breath and do something. All right? I'm going to do something. I don't know if it's going to be helpful or not, but I'm just going to do something. The issue is not to be helpful. The issue is to do something. So remember, this is the year 2017. That's something. I remember that. And I've got the 1st day, the 2nd day, the 3rd day, the 4th day, the 5th day, the 6th day, the 7th day, the 8th day, the 9th day, the 10th day, 11th day, the 12th day, the 30th day, the 40th day, the 50th day, what am I up to? I'm going to the 364th day, 365th day. There is no 366th day. It could happen, but 2017 is definitely not a leap year. 365 days. All right, so let's see. So one daughter calls every 3rd day. So they're all called on day 0. That was New Year's Eve. 1, 2, 3. Daughter number 1 called there. 1, 2, 3. She also called there. 1, 2, 3. Called there. Called there. Called there. So every 3rd day, grandchild, so not daughter, granddaughter called every 3rd day. Another granddaughter number 2 called every 4th day. Called on day 4. Called on day 8. Called on day 12. Called on day 16. But it's not on the list, and so on and so on and so on. And the 3rd grandchild called every 5th day. The 3rd grandchild called there on day 10, on day 15, 3rd one, and so on and so on. Okay, I'm doing something. That's good. I guess I could actually write out all 365 numbers and figure out how many were not called. So no one called the 1st day, no one called the 2nd day, no one called the 7th day, no one called the 11th day, 13th, 14th, and so on. I could do that, but that will take me forever. Okay, all right, so now my brain is racking, how can I avoid doing hard work? Because I don't like hard work. In fact, that's my definition of a mathematician, someone who will work very, very hard to avoid doing hard work. All right, so how can I avoid doing hard work? What can I do? Let's see. Well, okay, all right. I've got an idea. I'm going to engage in wishful thinking. Here's my next strategy, wishful thinking. I'm not sure if it's good or not, but I'm going to be wishful. Here's what I'm going to wish. I know that the 1st grandchild calls every 3rd day. So 2/3 of the day are not going to be, 2/3 of the times, 2/3 of the days, that grandchild is not calling. She's not going to call on those 2 days. not going to call on those 2 days. Of this group of 3, she's not going to call on those 2 days. So 2/3 of the time, 2/3 of the days of the time, grandchild 1 does not call. All right, so 2/3 of the time, grandchild 1 does not call. Now, of those days, grandchild number 2 calls every 4th day. So that means she's not calling 3/4 of the time. So 3/4 of 2/3 of the time, not 1 or 2, which are probably not quite right, but I'm being wishful thinking. I'm not worrying about the details. And grandchild 3 calls every 5th day. So 4/5 of the time, she's not calling. So for grandchild number 3, 4/5 of 3/4 of 2/3 of the time, grandchild not 1, 2, or 3. Terrible, terrible handwriting. But I'm going to guess roughly 4/3 of 3/4 of 2/5 of the time, 2/3 of the time, neither grandchild, not any one of the grandchildren is calling. And how much time is there? There's 365 days. So here's my wishful thinking answer. And you can probably say, but James, you're double counting or not double counting or whatever. I'm just going to go with it for now. Wishful thinking that 4/5 of, 4/5 of 3/4 of 2/3 of 365 days, no one is calling. No one is calling. And let me work that out. 4ths cancel, 3rds cancel. This is actually 2/5 of 365. 365, that's 350 plus 15. I can see the multiples of 5 there. So that's 2 times a fifth of 350 is 70. 73, 2 lots of 70, 73, 146 days. I'm going to say, if I had to make a quick guess, it's 146 days. That's no one's calling. Now, you're right. I'm sure I am missing some double counts. For example, day 12 was a double call, and this didn't allow for double calls. Day 15 is a double call. There's probably a triple call somewhere. Oh, actually, where would the triple calls be? Well, the triple calls had to be a multiple of 3 and a multiple of 4 and a multiple of 5. So the first triple call would be day 3, 4, 5. Multiples of 3, 4, 5, 12 times 5 is 60. Day 60 will have all 3 grandchildren calling. The first 60 will have all 3 grandchildren calling. Then the next 60 won't be to another 60 will have all 3 grandchildren calling. So this problem actually happens in blocks of 60. Oh, blocks of 60. Blocks of 60 is the way to go. So actually, maybe I can answer this question by actually writing out all 60. Well, am I really going to write all 60? Probably not. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Actually, you know what? I'm going to do it because you signed up to watch me write out all the numbers from 1 up to 60. How fun, how exciting to watch James Tanton do this. 29, 30. I'm halfway there. 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60. All right, okay. So let's see, I get rid of all the multiples of 3. There it goes, go, go, go. This is really tedious. All right, but this is actually illustrating another problem-solving strategy. Sometimes perseverance is the key. Just persevere your way through it. Where's 45, 48, 51, 54, 57, 60? There's all the multiples of 3 gone. Here goes all the multiples of 4, 8, 12 gone, 16, 20, 24, 28, 32, 36, 40, 44, 48, 52, 56, 60 already gone. Multiples of 5. Goodbye 5, 10, 15, 20, 25, 30, 35, 40, 45. Where is it? It's gone? 50 and 55 and 60 is already gone. How many survived? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 24 of them survived. Whoa! In that block of 60. So for every block of 60, 24 no calls. Okay, I think my perseverance is now paid off. Perseverance is the key. That didn't take me too long, and I could have been quicker by not actually bothering writing out all 60 numbers first. I could have skipped a lot of multiples off that. However, 24 days in each block of 60 of no calls. So the first block of 60, 1 up to 60, there are 24 days of no calls. Next block up to 120, 24 days of no calls. From 121 to 180, no calls. All the way up to 360, 301 to 360, there were 24 no calls. That's 6 blocks of 60. 6 times 24 days of no calls. That's 144 days of no calls. That's only day 360. I'm going to have to keep going. Oh my goodness. Oh, this is a crazy problem, but I can do it. 361, 362, 364, 364, 365. Oh, that's it. So there's 5 more days I need to consider. Which of these are multiple of 3? 363 is a multiple of 3. Which of these are multiple of 4? 364 is a multiple of 4. Which of these are multiple of 5? 365 is a multiple of 5. So there's 2 more days, plus 2 more days with no calls out of the year of 360 days. 146 days with no calls. You know what? I'm really proud of myself. Look at this. The wishful thinking said 146 days. This is insane. My wishful thinking answer turned out to be the actual answer. That is amazing. Okay, I'm actually kind of pleased with myself right now. That was actually kind of crazy. Whoa. But of course, this now begs a question. Does the wishful thinking approach, which kind of ignores double counting, always going to work? It's going to give you an approximate answer. Our approximate answer was so correctly approximate that it was actually exact. Is that a coincidence? Will the approximate answer always be exact? Or were we just lucky in this case? So there's a deep question. Will this actually always work out this way? In fact, again, because I'm someone who's 55 and I've had a lot more experience thinking about mathematics, I happen to know that this problem is related to a very deep theorem in mathematics, which is about something called the Chinese remainder theorem. But I'd like to talk about houses. Here I've got some houses. So here's my version of where this problem is based upon. So I had some experience in thinking about where this problem might be going, but here's how I like to think of this problem. Here's a row of houses. In fact, I've got 60 houses. And the roofs, alternate colors, orange, blue, yellow, orange, blue, yellow, orange, blue, yellow. All the roofs go orange, blue, yellow, and they repeat that cycle. So that cycles of 3, like the first grandchild. The doors go orange, blue, yellow, brown, orange, blue, yellow, brown, orange, blue, yellow, brown, orange, blue, yellow, brown. They repeat in a cycle of 4, like that second grandchild. And the chimneys go orange, blue, yellow, brown, green, orange, blue, yellow, brown, green, orange, blue, yellow, brown, green. They cycle in 5. So here's my question. Among 60 houses, like this, 60 houses, must there be a house? Must there be a house? Hang on, I need a better color. Pen. Must there be a house with roof that's blue and door that's brown and chimney that's brown? I want a blue roof, a brown door, and a brown chimney. Must there be a house like that? And how would you think about that? How would you think about that? So there's 60 houses in a row, the roofs cycle, the doors cycle, the chimney cycle, in cycles of 3 and 4 and 5 respectively. Must there be a house with those particular features? Now, of course, I'm in the unfortunate position where I can't actually see the chat or see you or have any means of interacting with you and see what you're thinking about. But the answer is yes. In fact, choose any combination of colors you like. There must be a house exactly like that. And then there's a nice way to see that. If you think about it, any 2 blue houses with blue roofs must differ by, must be like 3 apart. You know, house, blue, blue, and the 3 down is next blue one. Next 3 down, blue. So this must differ by 3. So any 2 houses with blue roofs differ by 3. Differ by 3. And any 2 houses with brown doors must differ by 4. There's a brown door, and you have to go down another 4 houses to see another brown door. Then you go down another 4 houses to see a brown door. So these must differ by 4. Differ by 4. So, or sorry, I should say just differ by a multiple of 4. So the roofs differ by multiples of 3. The doors differ by multiples of 4. And therefore, the chimneys differ by multiples of 5. If I've got a brown chimney here, I have to wait another 5 houses to get the next brown chimney, and then wait another 5 houses for another brown chimney. So any 2 chimneys that are brown differ by a multiple of 5. So any 2 houses that have a blue roof, brown door, and a brown chimney must differ by a multiple of 3, and by a multiple of 4, and by a multiple of 5. Well, there's only one possible multiple they can differ by is a multiple of 60. 3 times 4 times 5 is 60. So if any 2 houses have these features, they must actually differ by a multiple of 60. But there's only 60 houses. So there can only be one of them. There can only be one of them. There can be one of these houses amongst the 60 like this. However, I still haven't established that there actually is one. All I've shown now is if there is one, It has to be just one of them. But here's the thing. This argument works for any combination I like, which means, oh, how many combinations are there in total? Well, there are 3 choices for a roof color. There are 4 choices for a door color. There are 5 choices for a chimney color. So there's actually 60 choices in all. Oh, if we ever repeat a combination, then, oh, we have to repeat it within 60 houses. But we know we can't repeat a combination of 60 houses because they have to differ by at least 60. Oh, that does it. That means all 60 combinations must appear somewhere in the string. Bingo, bingo, bingo. So if ever you have a phenomenon where you've got something that cycles, we can say cycle of 3 or some number m, and something that cycles by another number m, and something that cycles by another number m, r or something, all within a system, then you can argue this way to say that every possible combination of those numbers must exist within that string, if the numbers are nice and don't have any common factors going on. Whoa, deep mathematics. This is the lovely thing about, as I said, the AMC is really a portal to deep mathematics. This is about a famous theorem in number theory in disguise. You've got to love it. So we still got time. Let's do another one. Why not? This is so fun. This is a fun one. Okay, let's go to 2019, just a couple of years ago. AMC 8, problem number 23. Again, another long one to read. Okay, here goes. After Euclid High School's last basketball game, it was determined that Alexa scored 1/4 of the team's points. Good on you, Alexa. Brittany scored 2/7 of the team's points. Good on you, Brittany. Chelsea scored 15 points. Chelsea, that's marvelous. Good on you. None of the 7 other team members scored more than 2 points. Okay, so there's these 3 people and 7 more team members. What was the total number of points scored by the other 7 team members? Oh, all right, so Alexa scored 1/4 of the points. Brittany 2/7 of the points. Chelsea actually 15 points. And everyone else got 1, 0, 1, or 2 points. And there's 7 other people. Okay. What's my emotional reaction? My emotional reaction is nervousness. This one actually got me nervous because I don't know the total number of points. So I'm told a fraction of points, an actual number of points, and something weird about these points. So I'm nervous. That's my reaction. Okay, step 1, done. Have an emotional reaction. Step 2, take a deep breath and do something. Do something. Do you know what? Here's my favorite way to do maths. I believe in pictures, the power of pictures. I'm actually going to draw a picture of this. So I'm going to let P be the number of points. P equals total number of points. And I'm going to draw a picture like this. The total number of points is actually distributed as follows. It's going to be some great big line of points, of which I know that Alexa, I'll just write A for Alexa, got what she got. She got 1/4 of the team's points. 1/4 of the team's points goes to Alexa. And Brittany got 2/7. 2/7 of those points go to, of the points, 2/7 of the P goes to Brittany. 15 actual points went to Chelsea. Sorry, 15 goes to Chelsea. Oh, ABC. Of course they chose ABC. ABC, that's very nice of them. All right, okay. 1/4 of the points to Alexa, 2/7 of the points to Brittany, 15 actual points to Chelsea, and there's 7 other people. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, and 7. And this is either 0, 1, or 2, 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 0, 1, or 2. Why do I write all that? I do not know. But that's the remaining points, Let's write R for remaining points. Okay, so there's a picture of the point structure. Oh, I guess that sort of suggests the equation. Like all the points equals 1/4 of the points from Alexa, plus 2/7 of the points from Brittany, plus 15 actual points, plus the remaining points, which the smallest it could be is like all got nothing. So it could be like, the worst it could be is 0. Or it could be all, everyone here got 2, so this could be up to 14, I guess, and everything in between. It's possible. All right, so I've got this equation. What do I want me to find? What was the total number of points scored by the other 7 team members? Oh, not the total number of points I want the total number of points scored by the 7 team members. Oh, I want the value of R. Okay, I want R. Okay, I've got this equation. All right, again, I'm a mathematician. I don't like hard work. I don't like fractions. So what I'm going to do is actually multiply through by something to make all the fractions go away. So I want 4ths and 7ths. So I'm going to multiply everything by 28. Why not? So 28p would be equal to 7p plus 8p, I think that's right, plus 15 times 28. I can't do that. 15 times 28 is something, plus 28r. All right, okay, great. 15p here and 28p. That makes 13p's is, still can't do 15 times 28. I'm not going to do it. Avoid hard work. And 28r. What am I going to do now? Actually, I'm glad I didn't work it out because there's a common factor of 28. 13p is 28 times 15 plus R. Okay, I'm not going to work this out. Okay, so what did I do? I had an emotional reaction. I decided to do something. I decided I like pictures of my friend. So I drew a picture of the points. That led me to an equation. I didn't like fractions in my equation, so I just got rid of them by multiplying with 28. I guess this is a good strategy. I'm just following my nose. I'm not sure where I'm going. I'm just playing around with stuff. I don't know if what I've done is helpful. Except. Here's another strategy for the AMC. It's about the author. I bet the author did something sneaky here. And I can't help but notice 13 is prime. Prime numbers come up a lot because they often are nice in arithmetic. For example, left-hand side is a multiple of 13. There's 28. There's no 13s in that. All that means 13ness is in here. This must be a multiple of 13. Must be a multiple of 13. Because that 13 is suspicious to me. So I am now second guessing the author. They wanted me to guess the number 13 appearing in my equation. So that means 15 plus R must be a multiple of 13. Okay, what are the multiples of 13? I'm just going to list them because that's all I can do. 13 is a multiple of 13. 26, 39, 52, and that's too hard. I'll stop there. Okay, which multiple of 13? Okay, I'm now really pausing. Oh, R is between 0 and 14. So we can't go too high. It could be 15 plus 0, or it could be 15 plus 14. So the smallest this could be is 15 plus 0 is 15, or 15 plus 14 is 29. So it must be a multiple of 13 between 15 and 29. It must be 26. 15 plus R is 26, which means R must be, if I can even do basic arithmetic correctly, R must be 11. 15 plus 11 is 26. Whoa. So that is crazy beyond belief. So we did it. Oh my goodness. All right, so now you're seeing how James Tanton's brains work. I make this sound as though it's all easy and I'm speedy. I am not speedy at all. I have very strong emotional reactions to problems. I do all the time. Sometimes they're positive ones, sometimes they're negative ones. Whatever it is, I'm human. I'm going to acknowledge my emotion and take a deep breath and try something. Drawing a picture is always very good. I like pictures. And then just followed my nose. I didn't really know what I was doing. I was just writing stuff out. And don't do any simplification. Well, first of all, make things look simple. If you don't like fractions, maybe get rid of fractions. If you want to make things simple for yourself, go for it. But at the same time, if something seems too hard, like 15 times 28, don't bother doing it. Just keep it as it is until you actually have to do that work. Avoid hard work. And I'm glad I did. Because this gave me a chance to do something else that's good in the AMC world, is second guess the author. Prime numbers mean something. For example, if you get a question that's about the number 243, you say, oh, okay, what's special about 243? Why do they choose that number out of the blue? No, let's make it 53 because I'm going to do my arithmetic correctly. Let's make it 253 because if I did that one, you say that's 23 times 11. Prime times a prime. There's got to be something special about 253, prime times a prime. Always second guess the author. All right, so what am I doing? Why am I sharing all this with you? Well, if you go to the MAA website, maa.org, there's something called Curriculum Inspirations. You'll see some really old videos of me actually going through AMC problems and showing you how my brain works. So I went through things very, very fast today. But there you also see little ideas and essays on the various strategies. I've identified 10 strategies that I think are really helpful for solving AMC problems. Apart from the key ones about being your honest human self, have an emotional reaction, take a deep breath, and try to do something. So we did all sorts of things. For example, we did this very first strategy. I call it engaged in successful flailing. For example, the very first problem we did today was this one about the rectangle in a semicircle. My flailing to get going was just say things about circles. And I said words like circle and perimeter and radius and diameter. And thinking about the radius got me going on that one. So I actually flailed around that one. I just played around with that one. I also just played around by drawing a radius there. Actually, you saw me first draw a radius there. I did actually draw a radius there. I remember actually drawing the second one. I don't know why, but I did. But I'm just flailing. That's okay. And then I eventually drew a radius there, and then we realized I used Pythagoras theorem. So just try stuff. Flail means just try stuff. Okay. Do something. Always do something. You might have an emotional reaction that's going to shut you down. That's okay. You're human. Take a deep breath and do something. You always do something. If you're not quite sure what to do, just list things about the problem, which is great. Definitely engage in wishful thinking. We did that today. I did that with the 3 grandchildren. 2/3 or 3/4 or 4/5 of the days had no calls. That was wishful thinking and it got me close to the answer. So close actually was the answer. That's amazing. Draw a picture. Even if a picture's already supplied, it was actually helpful for me to draw more to the picture by drawing that radius. So I drew that diagonal. But I also did that with the points problem. I actually drew a picture like this. This is what people call a bar chart in some early grade mathematics. It's great stuff. Pictures always speak 1,000 words. They always spawn 10,000 ideas. You've got to love math for drawing a picture. I also love the fact that I drew a picture. I wanted to keep playing. I didn't like the fact this was non-symmetrical. I actually drew the other half of the circle, and that got me to a whole universe of other questions. So drawing a picture is great. Keep drawing pictures. Pictures are the way to go. Solve a smaller version of the same problem. I didn't do that one today. But if you've got a problem about 100 people standing in a circle, try doing 1 person standing in a circle. Well, that's not very exciting, but try it. Then try 2 people standing in a circle, and then try 3 people standing in a circle, and work your way up. Because I bet doing smaller versions might see what's going on with the big version. Perseverance is key. We definitely did that one today. I listed out all 60 numbers. I don't know why you signed on to watch me list out all the numbers 1 to 60, but when I was doing that grandchildren one about phone calls, that actually helped me out. That got me going. That was a good question. Eliminate incorrect options. I certainly did that today with Baylor and Jen. I did not believe there was any dependence on that number n for that problem about choosing intervals. So I figured options C, D, and E were out, and I was right. That was great. That was a good move. Go to extremes. We sort of did that. I went to the midpoint. I had like midpoint of that interval seemed to be special. So rather than extreme, I went to special. Go to something special. And going to the midpoint was the key for Baylor's strategy for winning. Second, guess the author. We always like primes. If we see a prime, be suspicious. Something's going on about prime, most likely. And avoid hard work. Don't do calculations 28 times 15 unless you absolutely have to. Leave it alone because it might actually be helpful to see the 28 still around. Or if you don't like fractions with the fractions, multiply the top and bottom by whatever you like. Just avoid fractions. Grand. So they are 10 basic strategies that I've come up with that I think are really helpful for playing with AMC problems, whether you actually do it for the competition or just doing it for the fun of it, because I actually like the material on the AMC very much. Very rich, exciting stuff. It's all good stuff. And these are not only great problem strategies for mathematics, they're actually good problem strategies for life, especially do something. Don't let your emotions shut you down. If you're feeling stymied by something, okay, be honest, acknowledge your human self, take a deep breath. It's okay, and you can always do something. But that's my greatest wish upon the world. If we can teach the world to have the confidence when faced with a challenge in math, in life, anywhere, to acknowledge your fabulous humanness and to do something nonetheless, you'll actually start making progress to moving forward with that problem. That'd be great. So let me see if I can stop sharing my screen so you can see me now. Maybe you've been seeing me all along. Not sure how this platform works. There we go. I can see myself now. And I'm going to say thank you so much for coming today. I really appreciate it. I can now see you've been chatting away for all this time. Thank you for chatting. Now I can see your chats. And I believe someone might have a question for me about, a certain problem like I did right on the hour. Does anyone have a question for me that I started on the hour? Do you want to type in the chat now that I can see the chat? All right. Well, I'm going to stop there. In fact, I'm going to do the following. Oh, okay. I'm reading the chat. Background competition. I'm really passionate. Oh, there's a long message. Okay. And I'm going to get it again. Okay, excellent. Well, great. All right. Yes, the art of problem solving is also fabulous. A lot of materials there. In fact, there's many good resources all across the internet and, of course, across the planet. AMC is also got these great resources too. All is fabulous. All is good. And I think we should end off today with one more time a salute to the joy of mathematics. So let's all do the International Math Salute together one final time. It's how I started off the hour. Goes as follows. So put your coffee cups down and juice cups and water cups and sandwiches and muffins or whatever you're eating right now. Pens and papers down. Arms out front as follows. Here's the International Salute to Mathematics. I'm not making this up. This truly is a salute to mathematics. It's out there. Right over left. Then you go palm to palm. You wiggle your little fingers. You wiggle your thumbs. You wiggle your little fingers again. And then when you're ready, here goes. Just come on back. Whoa. If you tried that and you're wondering how I'm doing it, feel free to Google International Math Salute. You'll see that people all around the planet really are doing this, and you can be able to do it too. All right, one and all, this has been fabulous fun. Thank you so much. I will stay on a little bit longer if anyone actually has questions for me. Otherwise, have a fabulous, fabulous rest of the day. And I'll see you tomorrow when I do another session on the fabulous joys of AMC. All right, thanks so much, everyone. Best way to prepare for competitions in a short amount of time. Do you know what? I'm going to say the following. Do you know what? Just go and look at past competitions and read all the answers. I mean, try them for yourself, and don't make life hard for yourself. Just have a look at all the answers that people have. More than that, look at all the different ways people answer the questions. There's always more than one way to approach mathematics. So actually, it's really good to see what other people do. So if you're really doing this in a short amount of time, just read a lot and just dabble around. So just no shame in looking at the answers to problems. And you know what? You'll see brilliant, fabulous techniques, and some of them will stick in your brain, and you'll just have fun doing that. Also, when it comes to the competition, don't worry about the competition itself. As you saw, where is my question? I actually think a really good strategy for competitions is actually go in, find one question that seems to be really interesting to you. I don't know, this seemed like a little just basic question about geometry, but you saw that I got really quite intrigued by it. I actually went down Ptolemy's theorem. I went down about optimization problems. So maybe you can change your mind about what the goal of the competition is. Not so much to get a score that's going to be recognized by by whoever. Say, okay, I'm going to find one really interesting question in the exam. I'm going to stare at it for 20 minutes and actually memorize what the question is. And then after the competition, take it home with me and really play with it. And then I'm going to discover something interesting for myself. And then I'm going to email James Tanton and tell him all the things I discovered about this one question in the AMC. So that's a great strategy. So if you want to prepare for the AMC, I say, great. If you want to go for the points, for the fun of it, just read all the answers to previous exams. Just read them all of them. Or if you want to change the definition of success, find one question that seems to intrigue you and then play with it for the days and weeks after the competition, and then email me all the results and all the thoughts and wondrous ideas you had from that one problem. Then you've got one big fan from me for really thinking like a mathematician. That would be an awesome way to use an exam, use a competition. Cool. How to get solutions on your own? You know what? I know you said you keep reading solutions. Keep doing more of the same. Read. Yes. Or the other option is change the definition of what success is for the exam for you. I actually, I've got no trouble just spending a long time on one problem. That's how my brain tends to work, and that's fine. Some people are speedier than me. Okay, they're speedier than me. I mull and go deeper than on some other things. Great, I mull and go deeper on some things. So another approach is just change your mindset, what it means to take a competition. Just if you really want to get the points, because that means a lot to you, then I would say keep reading solutions. I know it doesn't seem like it's helpful to you. Keep reading more and more solutions. Obviously, don't just read the problem, then read the solution, read the problem, read the solution. Read a problem, mull for a bit, then read a solution. Read a problem, mull for a bit, then read the solution. Excellent. You go for it. Email me. Fabulous. You'll find me. I'm very easy to find on the internet. Great. All right. Time to move on to the next sessions, everyone. Thank you so much for coming today. I so appreciate it. Have a fine rest of the evening. Hopefully I'll get to see you tomorrow. Or actually, I get to not see you tomorrow because I don't see anyone. But hopefully you'll be here tomorrow and you'll get to see me. Thanks, everyone. Bye-bye.